Welcome to my video lecture on working on using the definition of Laplace transform on just calculating the Laplace transform of simple elementary functions. It's my third video lecture for module 4. So let's start with, as I said, looking into finding the Laplace transform of some basic functions like 1, e to the at, t, cosine of t, sine of t for to find f of s given those functions using the Laplace transform. And we'll start with using 1. So if my function is 1, just the most simple function, let's say f of t is 1, and I want to find the Laplace transform of that function. Basically, I'm trying to find a Laplace transform of 1. Now, recall the definition of Laplace transform. The Laplace transform of a function is the improper integral of e to the minus st, the function itself, and that's the kernel dt. So if I wanted to take the Laplace transform of 1, I have the definition here for you. It will be the Laplace transform of 1 times e to the negative st dt. Well, actually, there's a 1 right next to it. I already have it there, right here. And now integral of e to the negative st is minus 1 over s e to the minus st, and you're evaluating it from 0 to b as b goes to infinity. So you have minus e to the minus sb plus 1 over s as b tends to infinity. Now recall that if you don't know why it's what it is, I'll do some algebra here. If I multiply the top and bottom by e to the sb, I'll get minus 1 plus e to the sb divided by s e to the sb. Now, if you take the limit of this expression as b goes to infinity, you see this becomes minus 1 over s e to the sb plus, I separate fractions, e to the sb divided by s e to the sb. And if e to the sb's cancel out, and remember you're doing this limit as b goes to infinity, you basically have minus 1 over infinity, which tends to 0, plus 1 over s, where there's no numbers to plug in. So that's why the Laplace transform of 1 is 1 over s. So all that work we do for a simple Laplace transform of 1, it is the painful part of studying Laplace transform, just like when you study derivatives. First you use the definition, and then you used all the techniques of finding derivatives. Same thing is going to happen with Laplace. First we will use the definition to find the Laplace transform, and you should know how to find the Laplace transform of any given function by me using the definition. And then ultimately we'll learn how to use just techniques, and we don't have to every time use the definition to find the Laplace transform. And you'll see that as I go through the examples I'm going to present to you. So we've done the Laplace transform of 1, you get 1 over s. Let me focus on some geometric understanding of it. Let me just erase everything here. Okay, so now geometrically speaking, and I have the picture here, I used Mathematica to draw it. Remember, I'm taking the function f of t, which is 1. So if I draw the axes here, I mean this is the time domain, and this is f of t. So if I'm trying to find a Laplace transform of 1, f of t equals 1, so basically I'm trying to find a Laplace transform of a horizontal line. That's f of t equals 1. Now notice what happens to the Laplace transform when you find it. Now, of course, here's the command in Mathematica on how to find a Laplace transform. It's nice. You could use as a sort of a tutor or a calculator. You know, if you have Mathematica in the clouds, or you've purchased it as a student, or however you have access to it, you could always, whenever you're finding Laplace transform, you could always use Mathematica to check your answer to make sure you're doing it right. So you basically write Laplace transform of 1, comma, and then you write the original variable, which is t, and then the destination variable, which is s. And it simply gives you the Laplace transform, which is 1 over s. And we all know if you plot 1 over s, you get a hyperbola. So it's quite interesting, and mind you that this is the s-axis now, and this is the f of s axes. So you notice it's interesting that the Laplace transform takes a horizontal function and transforms it into a nonlinear hyperbolic function in frequency domain. So just an observation. Let's move on and actually now try to find the Laplace transform of a basic exponential. Well, Laplace transform of e to the at, but again by definition, is Laplace transform of e to the negative, is the integral of e to the negative st, which is the kernel, times the function, which is e to the at. This is a pretty easy integral, so I'm not gonna waste your time, video time with it. You should be able to do that integration, and it's very clear at that point to see that the Laplace transform of e to the at is basically 1 over s minus a, if you actually integrate that. And of course, you could also check with Mathematica, and you type find the Laplace transform of e to the at, and it tells you 1 over minus a plus s, or s plus s minus a. So there's the Laplace transform of e to the at. So from now on, everywhere you see Laplace transform of 1, and if you're not specifically being asked to show me how the Laplace transform is what it is, then you can just remember that Laplace transform of 1 is always 1 over s. So you don't have to go through this integration every time. And you also, from now on, remember the Laplace transform of e to the at is always 1 over s minus a. So eventually you'll be creating a list of Laplace transforms, basic Laplace transforms that you'll just remember, so you could ultimately use them to find future Laplace transforms without having to go through the pain of the definition. However, if you're asked to find a Laplace transform using the definition, then you should do it. Let's do one more set of examples. Now let's say I want to find a Laplace transform of a fundamental polynomial like just t. Now if I want to find a Laplace transform of t, that means my f of t now is t. So it's a linear equation. That's t, that's f of t, and that's f of t equals t. So I'm trying to find a Laplace transform of that. Now, by definition, Laplace transform is the function that you're trying to find a transform for, and the kernel, e to the minus st, so by definition. Now, of course, you could use u equals t, dv is equal to e to the minus st, then you could do du, which is dtv, which is minus 1 over s e to the minus st, and then you can do uv minus the integral of e du for integration by parts, but I will just use the tabular integration by parts to do it. So I could just write t e to the minus st, derivative of t is 1, derivative of 1 is 0, integral of so you differentiate the first column and integrate the second column, so you get minus 1 over s e to the minus st, and 1 over s squared e to the minus st. And then you multiply these diagonally and alternate signs, so you get minus t over s e to the minus st minus 1 over s squared e to the minus st, and you have to evaluate that from 0 to, I mean, usually you write infinity, you write b and then you do the limit, but I could just write infinity here, knowing that it's t that's going to infinity and it's t that's 0. And now if you evaluate both of these expressions at infinity, now mind you that this becomes minus t over s e to the, actually to make it a little easier guys, I could just factor out the minus 1 over s. So this becomes t over e to the st, and then plus 1 over e to the st, and that gets evaluated from t equals 0 to t at infinity. Now if you notice, this is minus 1 over s. Now this, as t goes to infinity, you see this is here, you see if we were trying to find a Laplace transform of a function that was stronger than an exponential when t goes to infinity in this situation, see, this is a perfect example and a perfect place for you to see why that exponential order definition exists, meaning that the Laplace transform isn't indefinitely convergible. I mean, now you can't find a Laplace transform of any function. You can only find Laplace transform of functions that as t goes to infinity, they don't get stronger than the exponential in terms of growth, so they could be bounded, they could be controlled. And the definition of exponential order we talked about, it becomes very clear here because, see, you have a t on top and an exponential at the bottom. Now, if this function that's on top, this f of t, that in this case happens to be t, if that function grew faster than the exponential, then this ratio here would not have gone to 0. And then the integral would not have had an answer, it wouldn't have converged. So you see the need for the function that you're trying to find a Laplace transform for to be of exponential order, which basically means to be able to be taken over by the exponential in terms of the speed of growth as t goes to infinity. So as t goes to infinity, this expression here goes to 0. And as t goes to infinity for the second expression, it also goes to 0. So you have minus 1 over s, so you got 0 minus, now you evaluate it at t equal to 0. Well, if t is equal to 0, you get 0 over 1 here, so it's 0, right? So I'll put it in parentheses, so 0 plus, and if t is 0 in the second one, you get 1 over e to the 0, which is 1, so you get 1. So this becomes minus 1 over s times minus 1. So you get 1 over s, right? For that. So here is, I did the t, right? All right, so yeah, I'm not going to use u and dv, so I'm just going to use the tabular way of doing integration by parts. So I have this created here. So let's, as I said in class before, the first sets are the derivatives and the second sets are integrals. So you put the t in differentiated, you put the e in integrated, and then you diagonally multiply them by putting the top as a plus and the bottom as a minus. Okay, so if I start my integration by parts, I'm going to get, I'm going to get minus 1 over s times t times e to the minus st. And then I'll get minus 1 over s squared e to the minus st. And I have to evaluate that from 0 to infinity. So remember, this is t equal to 0, and t, well, I can't say equal to infinity, so it goes to infinity. Or I have to put a b and say limit, so I just bypass that. Now, if I see me do this easier here, I have a minus 1 over s I can pull out. So I pull that out. So here I'm left with t divided by e to the positive st. And then plus 1 over s e to the st. And that ranges from 0 to infinity. Now, let's look at this. I have minus 1 over s on the outside. Now here, we're driving, so we're evaluating this expression here at infinity, and then we're evaluating it at 0, fundamental theorem of calculus. F of b minus f of a, you remember that. So now here's when it becomes apparent for me to be able to emphasize and mention earlier in the previous video when we talked about exponential order, and I said the only functions you can use that you could actually find a Laplace transform for them are functions that have to be of exponential order, which means they have to be able to be overtaken by an exponential. In other words, they can't grow faster than an exponential. That's what a function of an exponential order is. A function is of exponential order when it doesn't grow faster than the exponential counterpart as the variable tends to infinity. And that's a requirement in order for the integral to converge, which means it's a requirement for a function to have a Laplace transform. And I can show you that here very clearly, because you notice now if I'm going to replace t with infinity in the first expression, this t here will become infinity, this e to the st will become e to the infinity. Now if t grew faster than e to the st, then this fraction would not have converged to 0. So therefore, in order for me to use the function to find a Laplace transform, this is a process, the function I use must grow slower than the exponential grows towards infinity so that I could drive the whole thing to 0 when I'm actually doing the evaluations. So you clearly see that requirement right here in the action. So as t goes to infinity, the first fraction is so you have, evaluated at infinity minus evaluated at 0, and that will be my final answer. Now, evaluated at infinity, the first one is infinity over infinity, but de L'Hopital or whatever, we could say that that's 0 in this class at this point. So that's 0. Okay, plus, and then I replace t with infinity in the second one, so that's 1 over infinity, which is 0 also. Now, I evaluate both of these expressions at 0. So if I put 0 for t, I just get 0 over 1, which is 0, plus, and if I put 0 for t in the second fraction here, I get 1 over s times e to the 0, which is 1 over s. Now, if I clean all this up, I get minus 1 over s times minus 1 over s, which becomes 1 over s squared. And that's exactly what we found here. Of course, I skipped all this and I just put this on my PowerPoint because that, you learned that as the first lecture in the second semester calculus course. I just wanted to do it all out for you to just have seen it if you don't remember how it's done. All right, so, that's how you find the Laplace transform of t. So Laplace transform of t is 1 over s squared. So let me delete these. And now let's move on to the next one. Fantastic. So now someone would say, okay, now Laplace transform, I'm just going to write it here. Laplace transform of 1 is 1 over s. Laplace transform of e to the at I've learned so far is 1 over s minus a. And so far, Laplace transform of t I've learned is 1 over s squared. So I wonder, you could wonder as a student or as the student of Laplace transform or someone that's learning or studying Laplace transform, at this point you could be wondering, what would be the Laplace transform of t squared? What would be the Laplace transform of t cubed? What would be the Laplace transform of t to the fourth? Is there some kind of a pattern I could see doing this? Well, if let's say you don't, and you just point blank want to find the Laplace transform of t squared. Well, I'm going to actually do this with you guys. I'll never do it again, but I'll do it just one time. Second time, I've already done integration by parts once, but I'm going to, from now on my video lectures, leave out the integration by parts department since you guys could do that yourself. I don't need to do it for you. But I'll do this one as well, and then then we'll proceed and look at the pattern and if it exists. So now Laplace transform of t squared, again, t squared is of exponential order, obviously, because it doesn't grow faster than a parabola doesn't grow faster than an exponential. So I could find its Laplace transform, again, using the definition and using the tabular method of integration by parts. I have t squared and e to the minus st. So t squared becomes 2t, and then derivative of 2t is 2, derivative of 2 is 0. Integral of e to the minus st is minus 1 over s e to the minus st. I'm going to have you guys follow through with me. I'm hoping that you guys are at this point watching this video and taking notes at the same time, because just watching the video isn't going to cut it. Now let's continue taking the derivative again. So the integral again, you get 1 over s squared e to the minus st. And then you take the integral again, you get minus 1 over s cubed e to the minus st. And of course, we're going to have to diagonally multiply these entities, these derivatives and integrals, and also not forget to, that's not a good color to choose. Let's choose, green. So that's a plus, that's a minus, and that's a plus. So now if I go through the integration by parts process, I'll end up with minus t squared over s e to the minus st, correct, minus 2t over s squared e to the minus st, and I'm going to pause for a bit for you to see it. Okay, and the last one will be plus times the minus, 2 over s cubed e to the minus st. And I have to evaluate this from t equals 0 to t at infinity. Now, if I look at this and if I could pull something out, I could pull out a minus 1 again over s. I could pull that out, I see. So I could just then factor everything else inside the parentheses. So here, if I factor out a minus 1 over s, I'll end up with t squared over e to the st. And again, I'll write it as a ratio like that, so it's easy for you to see why at t infinity that thing goes to 0. Plus, and remember, you factor out a minus out of all of them, so they're all going to be plus, and 1 over s has gone out, so you get 2t over s times e to the minus st. And then plus 2 over s squared, because 1s goes out e to the st, and sorry, that's a plus, and that evaluates from 0 to infinity. Alright, so that's what I have so far. Now, keeping the minus 1 over s on the outside, okay, and then just basically evaluating the inside, I'm going to have to end up again with 2 parentheses with 3 fractions, each one for the infinity, one for 0. So here's my infinity group, and here's my evaluated at 0 group. Alright, now if I put infinity in these 3 fractions, so I put infinity in the first one, I put infinity in the second one, I put infinity, or drive those fractions towards infinity to see what happens. Again, since t squared is of exponential order, it grows slower than e to the st, so that whole fraction tends to 0. So 0 plus, second one here, in the second one here, I also see t is of exponential order, so it obviously grows slower than e to the st, so that goes to 0. And the third one definitely goes to 0. So now let's evaluate all 3 of these, and I'm going to change my parentheses color. So let's evaluate these now for the 0, and I'll here use a green color. So now for the 0, I need to evaluate the first one, the second one, and the third one at the same point. So if I put 0 for the first one for t, I'll get 0 divided by 1, which is 0. Plus, if I put 0 for the second one, I get 0. And if I put 0 for the third one, I get 2 over s squared times e to the 0, which is 1. And you notice that I'll ultimately end up with 1 over s on the outside and 2 over s squared on the inside. So the answer becomes minus 2 over s cubed. And I have a minus here. Oh, I'm sorry. There's a minus here I didn't see. My bad. So that'll be plus. I was wondering where that other minus is. It's very easy to make mistakes like that, so be careful. So, holy moly, Laplace transform of t squared, something as simple as that requires all this work, is by definition that. And of course, thank God for Mathematica. And when a lot of my students, when I tell them to learn Mathematica or to use it, the first question is, are we responsible for it for the exams and stuff? And it's really not a question of responsibility for an exam. It's a question of, it's a nice thing to know how to use or have it in your arsenal or in your tool bag. Like, for example, like right here, you're trying to see a pattern. Now look how much more work it is to go from t to t squared in terms of integration by parts. You could imagine what t cubed will be, or t to the 4th. So for us to sort of investigate to see if there's a pattern and try to do it all by pencil and paper, it's daunting. But if you had Mathematica, see, I mean, it's nice to practice and all that, but you really didn't need to do any of this. You could just, with Mathematica, you find a Laplace transform of t, which is 1 over s squared. Then you find a Laplace transform of like t squared, which is really not that difficult to type. It gives you 2 over s cubed. It gives you the same thing I found, but it beats all of this work. Then you find a Laplace transform. Now let's just explore. Let's see if there's a pattern. For now, I have, and let me erase all this extra stuff. Okay, so for now, based on my computations, I've done Laplace transform of 1 e to the at. Now I did the Laplace transform of t squared. And Laplace transform of t squared we found out to be 2 over s cubed. For now, I don't see that much of a relationship. I'm sure if I find t cubed and t to the fourth, then I'll begin to see it. But you see, if technology wasn't there, in order for me to see this pattern, I would have to do this by integration by parts. I would have to do this integration by parts. I have to do this by integration by parts. So for me to be able to see the entire pattern of what's happening as the power of t increases would have taken me like 2-3 hours worth of work and effort to just understand if there is a pattern or not. And you could see here clearly that if you had a technology available to you, you'd have just found the Laplace transform of t squared, Laplace transform of t cubed, which apparently it's 6 over s to the fourth. Then you find the Laplace transform of t to the fourth, which is 24 over s to the fifth. And at this point, you'd be in a position to be able to somehow figure out that, oh, it looks like the denominator, if power of 1, power of 2, power of 3, power of 4, but the denominator is always, it seems to be, you see, it's 2, it's 3. It's 3 goes to 4. If it's 4, it goes to 5. So you notice that the power of the transform is 1 higher than the power of the t function you started with. So there is a pattern there. And the numerator, 2, 6, 24, you should see those are factorials. 2 factorial is 2, 3 factorial is 6, and the 4 factorial is 4 times 3 times 2, which is 24. So you could see, oh my god, then I can clearly see that if I just wanted to find the Laplace transform of t to any power, it's just simply that power factorial divided by s to that power plus 1. So you see, you can, in 2-3 minutes, you could accomplish what you would have accomplished in terms of pattern recognition. It would have taken you 3-4 hours of hostile work to make that observation. So sometimes technology, not that you don't know, you should know how to integrate by parts, or you should know how to do all these stuff manually like I have and a whole bunch of generations before you have, but it's nice to be able to get to figuring out patterns and seeing patterns much faster using the technology available for you guys. So now I have a whole bunch of functions that I've taken the Laplace transform of, so I'm building a library of the Laplace transform of some fundamental functions. I will continue and do a few more on my next video. Thank you.